Okay, so let's move on to question number 10. What is the lattice energy of some metal halide Mx in the given the following information? So they give us the different enthalpy values for the heat of formation, electron affinity, ionization energy, dissociation energy, and sublimation energy. So it looks pretty intimidating, but I'm going to break down what each of these different values mean. So we're looking for lattice energy. And basically the definition of this is when you have your ions coming together to form your final solid or final like product. So in this example with the metal halide, this is when you have your positive metal plus a negatively charged halide to give our final product. Let's say it's Mx solid. So this is lattice energy. Now let's talk about the heat of formation. So this is the change in enthalpy when 1 mole of a compound is formed from its elements. So in other questions, they might define the heat of formation as kind of like the net, delta H net of the reaction. So for our example, this is the same thing as having our metal as a solid plus our halide as a gas. So these are just the pure elements to make our final product. So this is what I mean by like it's the net of the reaction, because this is basically our final reaction. And all of these little steps are how we would make our final product. Okay, so that's heat of formation, electron affinity. The definition of this is the energy change that occurs when an electron is added. So in our example, this is when you have our halide as a gas plus an electron, and then it ionizes our halide to get X minus. So similarly, you can also have ionization energy. So some people like to see this as like the opposite of electron affinity, because this is the amount of energy needed to remove an electron. From an atom. So in our example, that's when you have our metal as a gas already. An electron is removed, and that's how our metal becomes positively charged. Okay, so moving on, dissociation energy. Dissociation energy. Basically, it's the energy that's needed to break bond. So in our case, let's say we have our elemental halide. To come up to break them apart is dissociation energy. Okay, so I'm just going to start a new page to write down the definition of sublimation. So sublimation sounds complicated, but it's actually pretty easy. It's the energy needed to convert solid to gas. So I remember it as they both start with S, like solid and sublimation. And in our case, it's when we have our pure metal solid and we are converting it to a gas. So now that I wrote out all of the different steps, I can make this into a Bourne Haber cycle. Okay, so again, let's recall that our net reaction is our metal solid coming together with our halide gas to form a metal halide as a solid. The energy that it took to get to that net equation is called the delta H of formation, which was equal to negative 500 kilojoules. So that's why I had an arrow going down. So in order to get from our elemental solids and gases, we first need to convert our solids to gas, and then our gas needs to be ionized. So I'm going to write it out like this. So I'm going to do an up arrow to show that we need energy. I'm going to show that our metal solid needs to first be converted to the gas. So this is called sublimation. And this had a value of positive 550 kilojoules. So now that we have our metal as a gas, I want to convert my halide to a gas, but I first need to, well, it is a gas, I first need to break apart the X2 bond. So I'm going to write out that the bond dissociation needs to occur just to get a halide on its own. And this required 300 kilojoules of energy. And then what also requires energy is ionizing our metal to make it positively charged. So we have now our metal as a gas, and then it will be ionized to M plus an electron. So this is ionization energy, and it has a value of 700 kilojoules. So those are all of our positive values. I'm gonna draw the other half of our Bourne-Haber cycle. So going down, what released energy was our halide gaining an electron to become negatively charged species. So this released 400 kilojoules. And what also released energy is the value that we're looking for, called lattice energy. So again, just to refresh, this is when we have our ionized metal, our ionized halide coming together to form the final product, MX solid. So here you can see that our cycle is now complete. We took our raw elements, converted the solid to gas, and then ionized the gases. And then once we have the ions, they come together to form our final product. So this can be written as an equation where you have your delta H of formation is equal to the sum of all these different energy steps. So again, delta H of formation is equal to delta H sublimation, dissociation, ionization energy, which can occur in more than one steps. Same with electron affinity, it can occur in multiple steps. And finally, lattice energy. So now I can rearrange this equation to solve for lattice energy, which is what the question is looking for. So I'm just going to move all of these values to the left, so they all just become negative. Okay, so now I'm going to plug in all these values. Delta H of formation was negative 500. Delta H of sublimation was 550. Delta H of dissociation was 300. Ionization energy was 700. And then the electron affinity was minus 400. So if we add all these values together, you get minus 1,650 kilojoules as our delta H. So you also know you did it right because the delta H, your lattice energy, is typically always negative. Since the ions coming together is favorable. So this is the same thing. It's 1650 is option C. Oh, 3. Sorry. Option 3. So let's see what our junior tutor said. Third option. Explanation is lattice energy is an estimate of the bond strength in ionic compounds. It is defined as the heat of formation of ions of opposite charge in the gas phase to combine into an ionic solid. It is used to explain the stability of ionic solids. To calculate the lattice energy of an ionic solid, Bourne-Haber cycles can be applied, and the concepts of ionization energy, electron affinity, dissociation energy, sublimation, the heat of formation, and Hess's law should be understood first. So this is why I also wrote down all the definitions. Ionization energy is the energy required to remove an electron. Electron affinity is the energy released when an electron is added. Dissociation energy is the energy required to break apart a compound. Sublimation energy is the energy required to case a change. I guess it's required to change the phase from solid to gas, bypassing the liquid phase. Heat of formation is the change in energy when forming a compound from its elements. And then Hess's law states that the overall change in energy of a process can be determined by breaking down into steps, then adding the changes in energy of each step. So that's what we did in the last part here. So the Bourne-Haber cycle is essentially Hess's law applied to an ionic solid. The Bourne-Haber cycle can be reduced to a single equation where heat of formation is equal to heat of atomization. So this is the same thing as the lattice energy. Oh, I know. It's the same thing as when you atomize one of the gases, I believe. Dissociation energy, so that's breaking apart the halide. Plus the sum of ionization energies, plus the sum of electron affinities, plus lattice energy. Oh, okay. So heat of atomization is the same thing as sublimation. So then they also rearranged the formula for lattice energy. So they did lattice energy is equal to heat of formation minus sublimation minus dissociation minus the sum of ionization energies minus the sum of electron affinities. And then they also got minus 1650 kilojoules. I'm just going to say this solution is correct.